Hi everyone, welcome to Unit 2, and we are starting today with Lesson 9.1. This is going to be found on page 119 in your Springboard books. Before we get started on page 119, I wanted to bring to your attention this little warm-up activity here, where you're looking at these data points and deciding are they increasing, decreasing, or neither, and if it is increasing or decreasing, what kind of relationship is it? Is it linear? Or is it nonlinear? So take a moment to look at these examples and decide those couple of things. So what you may be noticing here is in this first example, it is increasing, but it is not a linear increase, right? There's not a consistent adding or subtracting amount here, so that's not linear. Number two, while we are decreasing for a little bit, we end up increasing as we jump from 4 to 5 because we're going from 1 up to 10, then back down to 7. So this is an example of a graph that is neither increasing nor decreasing. Number 3, we are consistently increasing by a value of 4, so that would be a linear graph because we're adding 4 each time, and 4, we are subtracting 5 each time, so we are decreasing in a linear way. Okay. Now what this leads us into is today's lesson, in that the idea that we want to determine what's our best data type, our best model type for given data. So we're going to look into different types of polynomials that we might best use, and it's really handy if you have your calculator available to follow along with a lot of these problems when it comes to the regressions. So if we look on page 119, finally, we are given a table of values, and these are representative of the sunspots that are observed on the surface of the sun in the years since 1990. So what we're seeing here is just an increase of each year, kind of the years since 1990 are what's being represented, and we have then the number of spots for that year. So what I want you to do is answer number 1 and number 2. Would a linear function best represent this data, and or would an exponential function be a good model for this data? What you hopefully observed is that a linear function is definitely not appropriate here, right? It's not appropriate because we are not getting that consistent value that we are either adding or subtracting every time. In fact, we are decreasing up until we get to the year 1997. We're going to notice that we're going to shift to start increasing. So we have a decrease and then we have an increase. So it's definitely not linear because we don't have that. And this is also going to not be exponential. And the reason is because there's not a constant multiplicative change, right? So we do not have a constant multiplicative change, okay? Does not happen, right? So no constant multiplicative change. So what that's basically saying, again, if we divide our two consecutive terms, 94 divided by 146 is not going to be the same thing as if we divide the next two consecutive terms of 55 divided by 94. So term 3 minus term 2, not going to be that same multiplicative rate. We can kind of keep seeing it happen. Term 4 divided by term 3, it's not constant. It's close, but it's not constant. So it's not going to be exponential as well. If we graph these points, okay, so if we set up these first 10 years and go up, graph maybe up by 20s, what we're going to see here is that this graph actually has a quadratic look to it. And the reason being, it kind of looks like a decreasing parabola. So we would say that this looks like a quadratic, right? And the reason being it looks like a parabola with a minimum value. Okay. Now, the next piece then allows us to best fit the a model that could best fit this quadratic using those data points. So if we use the data points from page 119, reminder, we can take our calculator, if we go to the stat menu, and we can edit it so that our list includes these data points. So years 1 through 10, and then our number of sunspots. And what we can do then is create a regression to fit this. So, oops, I want to zoom. Go back into the stat menu after you have your data typed in, and you're going to calculate, in this case, a quadratic regression. So option 5. And what we're going to see here is an approximation for our quadratic formula, or for our quadratic, equation. And if we type this in, we end up with 6.01 squared minus 67.513x plus 204. I'm going to change my window so that I'm going from 0 to 10, and then up by ones. We'll start at 0, go up to 200, go up by 20. And I'm going to just to look at the data pieces, I'm going to turn my stat plot on. So we see here those data points that we have graphed, and we see this quadratic graph, so we can kind of see that fit here. Okay. So again, the steps for that then are stat menu, calculate, and then option 5, in this case, a quadratic regression to get the line. And again, what we see here, some important features are that this is symmetric. It does have that quadratic aspect to it. It's going to open up. And finally, we have then a minimum value, which if it's an upward facing parabola. So we want to look for that minimum value. So we go back to the calculator. Something we could do is if we hit second trace, we're going to get the calculate menu, and we can calculate that minimum value. So let's say if we approximate it, let's say 4 is a bound. The right bound we'll say is 7. And then we're going to scroll to somewhere in between there. Enter a couple of times so that we get that approximation that our minimum value is occurring at 5.6 and the minimum number of sunspots about 15.4. So we would say that the minimum is going to be located at 5.6, 15.4. That's where our minimum's at. And speaking of minimums, good time to talk about some of the vocab for this unit. When we talk about a relative min, that's anywhere we see minimum values as well as relative max. And then those relative mins and relative maxes, those are known as our turning points. Okay, so that minimum is actually going to be helpful to us if we look at the bottom of page 120. In what year are the sunspots at a minimum? That's at year 5.6. Again, looking at that model, aka that's going to be about halfway through 1995, 1996 time frame, if we're talking years. Which then means if we're looking to figure out when will the number of sunspots be 200, well, that's where we're going to set our model equal to 200. So that's at the top of page 121. We're looking to take our model and ideally find when is this equal to 200. Which, if you think back to last unit, in order to solve this for x, we're not going to have a nice, pretty factorable value. If we subtract the 200 over and get 0, then really we're going to have our model and we're going to be able to use the quadratic formula in order to be able to find when the values are going to occur. Now you should have gotten, if you look at the quadratic formula, you have our lovely friend x equals negative b plus or minus square root b squared minus 4c all over 2a. That ends up happening is we have the two answers of about 11.157 and the second answer of 0.074. So that's basically telling us that in 2001, 11 years after 1990, or 1990 itself, so it's not even a year beyond that, would be when the value is going to equal 200. Okay. Now, this last piece here, then, number 9, asks us if we really think a quadratic model is accurate for this. Well, if you think about the distant past, years before 1990, or the future, probably even now, it doesn't really make sense because the number of sunspots would be extremely large, right? So it doesn't really make sense that that would be the best model, just given the nature of these extremely large. Extreme. I don't know why I was trying to put an A in extremely large. Okay, so it doesn't really make sense. All right, which leads us to the next piece then. If we took 5 more years worth of data, okay, and graphed this image, what we're going to see is that our quadratic turns again to have another relative max. Notice that that vocab word is on page 121 here. This is going to end up having a relative max, which means that a quadratic is no longer the best equation. In fact, what you probably end up seeing is that a cubic function is going to be our best way to model this. And the reason being is because our data appears to have 2 turning points. 2 turning points. Whoops. And again, we do have the ability to use our graphing calculator to find that regression. So what we're going to need to do is we're going to add on to our list the next number of years, right? So 11, 12, 13, 14, 15, add on the number of sunspots, and take a moment to calculate then the cubic regression. Well, what you should see is when you calculate said cubic regression in your calculator, we end up with a cubic answer, right, to the 3rd degree. And this time, I'm going to turn my plot off. What we're going to see is that that equation comes out to be negative 0.05x cubed 14.937 squared, and then minus 103.359x plus 239.810. And I'm going to extend my window a little bit further so that we see, and then I'm actually going to make this a little bit on the negative side, because what we're going to see here is with this cubic, our graph doesn't quite, it's gonna come with this cubic. We're gonna see those 2 turning points. We're gonna see it eventually kind of cross over what looks like in the future over our x-axis, so we would have a 0. And we can look at this because our y-intercept here is going to come where we plug in 0 for x. So according to this, if you're plugging in 0 for x into this equation, really what's going to happen is we're going to see where we touch the y-axis is really just going to always be this last number here. Because everywhere else where 0 is plugged in, this all basically becomes irrelevant. And we see that it's right around 240. And again, another way to double check that, look at your table. 0, we're at 240. Some other important features besides your y-intercept of 0 to 40, you would want to look for any relative maxes or relative mints, which again, you could calculate those using the second calc to calculate maxes and mins, similar to how we did before. you're going to be able to calculate zeros. In this case, we probably would have to extend our graph just a little bit more so we can actually see where it crosses. But there is a 0, and you're going to calculate that very similar to how you calculate your maxes and your mins by using the calculate menu here and by hitting second trace. And you'll see 0 is an option. And again, you can type these in to be able to see, okay, where exactly does my 0 or my x-intercept occur. Oops, did not take true left bound on that one. So if we calculate the 0, 14, right bound will go 17, and then that guess is somewhere in between there. And we see that about 15.1 would be our 0. So we have all these pieces that we can start looking at. And again, I'm going to just save us some time. So we have a max, a relative max at 11.4, and then 106.4. We have a relative min then, much lower than that at 20.8. And we call these the relative ones because obviously the graph goes negative to infinity, but we see that min, that turning point. And again, speaking of going as x goes to infinity, our graph f of x goes to negative infinity, right? If we look at this graph, it's going to negative infinity here as opposed to when we go as the x gets more negative. So as it travels to negative infinity, our graph is actually heading to positive infinity on the other end, okay? Now, again, does this make sense for 25 years down the line that this graph is going to make sense? And the answer is no. We're probably not going to have a negative number of sunspots. It's not going to be possible. Okay, kind of your minimum is 0. So this model is not necessarily making the most sense. And also, especially when you consider, like, okay, if I was trying to figure out how many sunspots were going to be observed in 200 BC, well, if we started this graph in 1990, that means that the 200 BC is going to be represented by an x value of negative 2190. And if we tried to calculate that, I don't even know if our calculator is going to let us. If we tried to type in negative 2190, it's going to give us, a valid answer. If we typed it into the actual equation, it actually comes out to be like a crazy large number. If you type in f of negative 2190 into the actual equation itself, you're going to get like 6.4 times 10 to the 9. So a huge number. Doesn't seem like that that was probably our case in 200 BC. So really probably overall for this particular example from the book, something with a sinusoidal regression would actually make the most sense to us. But that's not a polynomial, so not necessarily even the actual answer, but for the case of this, again, just looking at those turning points to help us decide what kind of polynomial our graph would best be. Okay, so to summarize some things, make sure that you know how to kind of type in the data and run regressions. Big thing here is to look for your turning points, okay, because that's going to help you determine if there's one turning point, you probably are going to want to use a quadratic versus 2 turning points where that was a cubic, 3 would be quartic and quintic and so on and so forth. Okay. Thanks everyone, and see you in class tomorrow.